Howdy, and welcome to a Mean 315 auxiliary lecture, where in this lecture what we are doing is we're calculating the steady state non-work properties, or we're calculating the properties of a steady state non-work device. And basically so of course there's several devices that we talked about that are steady state non-work devices: nozzles, diffusers, throttles, mixing chambers, pipe flow, duct flow heaters, and heat exchangers. In this particular one, what we're studying is, of course, a mixing chamber. So we have water at 65 degrees Fahrenheit and 20 psia, and it's heated in a chamber by mixing it with saturated vapor at 20 psia. So, of course, the water at 20 psia is at a much higher temperature than at 65 degrees Fahrenheit. We're told that if both streams enter the mixing chamber at the same mass flow rate, determine the temperature and the quality of the exiting stream. Okay, so I chose this one because I wanted to essentially illustrate how we can use all of the information that was given to us in Lecture 15 in terms of all the various steady state devices, all the assumptions, typical assumptions, things like that, how we can use that information to basically apply it in some kind of an example. Okay, so we're going to apply the various assumptions that we were told in the lecture on how to do mixing chamber analysis. Okay, but the methodology is pretty much the same, where we start by drawing our control system, right? So as was drawn, we have our mixing chamber, which basically looks something like this, right? Where we have an inlet flow, which we're going to call this inlet state. This will be state 1, right? And the second inlet flow, which we'll call state 2. And then our exit state, which we will call state 3. So that's our control system. And then once we draw our control system, I like to write down the state information that we have. So for state 1, we're told that the temperature is 65 degrees Fahrenheit and the pressure is 20 psia. Okay. And then we're also told at state 2 that we're a saturated vapor, right? Which means that the quality at state 2, x2, is equal to 1.0. Okay, this is saturated vapor. And then we're also told that the pressure at state 2, P2, is equal to 20 psia. Okay. Now we also have state 3, but we don't have any information about state 3 from the problem statement. So state 3 right now is a big old question mark. We just don't know anything about it just yet. Okay, so now after we write down our state information, I like to write down information about the process, right? So we have a steady state mixing chamber. Okay, that's the kind of process that we have. And the other piece of information that we're told about the process is that the mass flow rate of the first inlet flow, m.1, is equal to the mass flow rate of the second inlet flow, m.2, right? So, for example, we're told here, right here, that the two flows have the same mass flow rate. Okay, so m.1 is equal to m.2. Okay, that's where that comes from. Okay, now we can write down what it is that we need to find, right? So after we write down details of the process, we write down things that we need to find, and we're basically asked to find the temperature at state 3 as well as the quality at state 3. Okay. Okay, so we can go ahead and move into our assumptions now, right? So, which is to say that we can move into our analysis, right? And so the first thing that I like to do when we start the analysis is to remind ourselves of the assumptions. Okay, and so the first assumption that we're making is that this is, of course, a steady state, steady flow device, right? So steady state device. And then the second assumption that we can make for our mixing chamber is that it's adiabatic, right? Remember some of the typical assumptions that we can make, one of the typical assumptions that we can make for a mixing chamber is that it's adiabatic. And so in terms of any thermal energy transfer between the system and the surroundings, that Q will be equal to 0. Now, the third assumption, there's a third assumption that we can make, and again, this is why we need to rely on that information that was given to us in Lecture 15. The third assumption that we can make is that typically the flows all have the same pressure, right? And that is going to be true in this case as well. We were told explicitly that state 1 pressure and state 2 pressure are the same. And so that gives us a very good reason to believe that state 3 pressure will be the same. In fact, the only reason why state 3 pressure would be different is if there was some kind of a pressure loss through the system, right? Like if there was internal flow friction or some kind of a resistance inside the mixing chamber that would cause P3 to be lower. P3 can't be higher than P1 or P2. That would technically be a violation of the second law, unless there was some kind of energy transfer into the system that caused P3 to be higher than P1 or P2. And since we're not given any details of that information, and we certainly wouldn't expect it with it being a mixing chamber, that's not what a mixing chamber is meant to do, we can only assume that P3 is equal to P1 and P2, right? So the flows all have the same pressure. That's one of our typical assumptions for a mixing chamber. Which is to say P1 is equal to P2, which is also equal to P3, right? So where the assumption is coming in is right here, since we were told explicitly that P1 is equal to P2 from the problem statement. Okay, very good. So now, now that we have our assumptions out of the way, we can go ahead and proceed to do our analysis, right? And what's the first thing that I ordinarily like to start with is the first law, but because this is a multiple flow in and out, right, or at least multiple flow in, I'm going to go ahead and start with the conservation of mass this time, okay? And so ordinarily, you know, in my mind or in our minds, we might think to start with the conservation of mass, but in a lot of our situations that we encounter, it's single flow in, single flow out, so the conservation of mass is really trivial. But in this case, it's not, right? We have two flows in, so our conservation of mass tells us that the sum of, for a steady state system, m dot I is equal to m dot E, okay? And so what that tells us for our control system is that m dot 1 plus m dot 2 is equal to m dot 3. And now we just remember, right, we can recall that m dot 1 is equal to m dot 2, right? That's basically in the statement, the problem statement, okay? And so that means then that we can say, for example, 2 m dot 2, or 2 m dot 1 if you want, is equal to m dot 3. So we could just as easily say 2 m dot 1 is equal to 2 m dot 2, which is equal to m dot 3 based on conservation of mass. Okay, that'll be helpful coming up later on, but for now, let's then proceed into doing our first law analysis. Okay, and again, we could cut right to the chase and look at our typical first law equation that we developed from lecture 15, but I'll just go ahead and start things from the top so that we can see how this stuff is derived. So of course our steady state first law equation, right, neglecting kinetic and potential energy, so I'm already imposing that assumption into our analysis, is equal to W dot plus M dot E HE, right? And this is a non-work device. Mixing chambers aren't meant to transfer work, so this term is equal to 0. And applying one of our typical assumptions for a mixing chamber is that it's adiabatic, so Q dot is also equal to 0. The sum of M dot I HI, of course, is just M dot 1 times H1 plus m dot 2 times h2, and the sum of m dot e times he, well, there's just one term on the exit side, m dot 3 times H3. Now we can apply our conservation of mass result, right? So we apply conservation of mass, and we find that since m dot 1 is equal to m dot 2, right, we can simply write this as m dot 2 times H1 plus m dot 2 times H2. And from the conservation of mass, m dot 3 is equal to 2 times m dot 2 times H3. So now we have m dot 2 appearing in every term, so that cancels out. And our first law equation tells us that H1 plus H2 is equal to H3. And now, if you notice, all of a sudden, we have a means to determine H3. H1 is known, state 1 is fixed, we're given two independent properties at state 1. State 2 is fixed, H2 is known, we're given two independent properties at state 2. And so we have H3 is the only unknown in this equation. One equation, one unknown. We can go ahead and use our first law equation to solve for H3. Okay, so in order to do that, let's now focus on determining our state 1 properties. So our state 1 properties are 20 psia, and T1 is equal to 65 degrees Fahrenheit. Okay. Now, again, first thing is just like we did early on this semester. First thing that you want to do is you want to figure out what phase you're in, so that you know what table to look your properties up in, right? So if you just think about this, right, you have water at 20 psia at a temperature of 65 degrees Fahrenheit, right? Water at 14.7 psia boils at 212 degrees Fahrenheit. And if you increase the pressure, which is what we from atmospheric, right? So we went from 14.7 psia up to 20 psia. We've made it even more of a compressed liquid, and we're well below 212 degrees Fahrenheit, right? So that clearly makes, water at these two properties, water at this condition, is going to be a liquid, right? So we have liquid water. Okay, now if you didn't follow that, or if you're thinking, all right, look, I really don't know water well enough to be able to look at those two properties and say that I have liquid water, don't worry. Use one of the techniques that we talked about early on this semester, where you can either look up the saturation temperature at 20 psia and verify if T1 is above or below that. If it's above it, then that means that the water is superheated vapor. If it's below it, then that means that water is a liquid, right? So let me write this down. Okay, so if Tsat at 20 psia is greater than T1, then your substance is a liquid, right? In other words, the substance is below the vapor temperature, the saturation temperature, the boiling temperature. Or if Tsat at 20 psia is less than T1, then your substance is a vapor, right? In other words, your substance is above the boiling temperature, okay? Or, now you can do it by looking at pressures too, right? In other words, if Psat at a temperature of 65 degrees Fahrenheit, okay, is greater than P1, in other words, the pressure of your substance is less than the saturation pressure of your substance at that temperature, right? That means that you're a vapor, right? You're at a lower pressure than the saturation pressure, and so you will have boiled. Or conversely, if Psat at a temperature of 65 Fahrenheit is less than P1, well, now you're compressed relative to the saturation pressure, so then that means that you are a liquid. Okay? Either or. Either one that you want to use, to just so long as you're able to identify eventually that this is liquid water, then you're in good shape. Okay, so now that we've established that state 1 is liquid water, we can then say, okay, well, I know which table to go look up my properties. I have my compressed liquid properties. But the problem is, again, right? So now we have another concept that we've learned already that we're relying on again. If I go to table A7E, which is my compressed liquid table, right? So I've established that I'm a liquid. So my reaction is to go to the compressed liquid table. What I unfortunately learn is that the lowest pressure, right, P min in table A7E is 500 degrees Fahrenheit, or excuse me, is 500 psia, which is much, much greater than P1. So now what do I do? Well, in this case, this is now when I can apply what I call my saturated liquid approximation. Which basically says that I can assume properties of liquid water, or of the liquid substance, right, of liquid, are the same as saturated liquid state at the substance's temperature, right? So, by applying our saturated liquid approximation, that means that H1 is equal to the saturated liquid enthalpy at a temperature of 65 degrees Fahrenheit. And when I look that up in table A, so now I'm going to table A4 because I'm looking up saturated properties. Table A4E, I find that for water at 65 degrees Fahrenheit, its enthalpy, saturated liquid enthalpy, is 33.08 BTU per pound mass. Okay, and I get that from table A4E. Okay, so if I look at my first law, I only need H1, so I don't need to write down any other properties here. So we'll go ahead and just leave it at that. Okay, so I can then go to my state 2 properties. And so what I know at state 2 is that P2 is equal to 20 psia. That was given to me. And then I was told that I am also a saturated vapor. So my quality at state 2 is 1. That's my saturated vapor state. And so H2 is also easily looked up. That's just the saturated vapor enthalpy at a pressure of 20 psia. And when I go to table A4E, table A5E this time, since I'm looking it up by pressure, I see that my enthalpy is equal to 1156.2 BTU per pound mass. And this is table A5E. Okay. Okay, so so far easy enough. I now have H1 and I now have H2. So my first law equation can be employed to give me H3. So I'll go to a new page here. And we can then calculate that H3 from our first law is equal to H1 plus H2 divided by 2. And when I plug these numbers in, H1 is 33.08 and H2 is 1156.2. This is all divided by 2. And when I plug that into the calculator, I get a value of 594.64 BTU per pound mass. Okay, so that's H3, but I was asked to find my temperature and my quality at state 3. Okay, so not just enthalpy at state 3. And so I then need to come up with my state 3 properties. So far, I only have one independent property at state 3. So my state 3 properties are as follows. First, I just calculated H3, right? And so we're saying that H3 is equal to 594.64 BTU per pound mass. Okay. And my second independent property, now I apply that third assumption that I made, which is that P3 is equal to P1, which is equal to P2, right? I made the assumption that all of my pressures are equal to each other. And so P3 is also equal to 20 psia based on that assumption. Okay. So now if I go to table A5, what I'll learn is that Hg, right, my saturated vapor enthalpy, so Hg at 20 psia is roughly basically is approximately 1150 BTU per pound mass, okay, which of course is greater than H3, okay, and H3 is greater than HF, which is 196, about 196 BTU per pound mass. And so this result here tells me this result here tells me that state 3 is saturated. The fact that we're being asked to calculate quality is a clue, but it's always good to be able to verify these things anyway, right? Because you have to know what properties to look things up in. Okay, so we know state 3 is saturated, so that real quickly allows us to easily answer the question of what is T3, right? What is the temperature at the exit state? Well, T3 is just equal to the saturation temperature at a pressure of 20 psia, okay? And so when we go to table A5e, we find that that saturation temperature is 227.92 degrees Fahrenheit. So that's equal to T3. That's one of our first final answer. Okay, and I get that value from table A5e. And now the last question is, or the last item that we wanted to find is what the quality is. And so to determine quality, we use our quality equation in terms of enthalpy, where H3 is equal to HF plus our quality at state 3 times HFG. Okay, and so we can just algebraically manipulate this so that we're solving directly in terms of quality. X3 is equal to H3 minus HF divided by HFG. And I can look these two values up in the table. So my saturated liquid enthalpy at a pressure of 20 psia is equal to 196.27 BTU per pound mass. And HFG, my enthalpy of vaporization at 20 psia, is equal to 959.93 BTU per pound mass. And I got both of these values here from table A5e. Okay. And now I can go ahead and plug all of this into my quality equation, where I get that X3 is equal to H3, which we calculated to be 594.64, minus HF, which is we looked up to be 196.27, divided by our HFG, which is 959.93. And so then we can plug this into our calculator and get a final answer for quality. Which is 41.5%. So, in our mixing chamber, we took something that was saturated liquid, that was the one stream, and we took something that was superheated vapor, or well, excuse me, saturated vapor, that was the second stream, and we combined them and we came up with something that was actually a little bit less than 50% quality. So there's an important concept that's embedded in this number, right? Think about this for a minute. The one stream, okay, so one stream was saturated liquid, okay, at a temperature of 65 degrees Fahrenheit. And the second stream was saturated vapor at 20 psia, but you know, because it was saturated, we can say that it was at 227.92, okay? And when we mix them, the exit stream has the same temperature as the 227.92, right? And so correspondingly, our quality is less than 50% because some of the energy to vaporize the first stream first went into raising its temperature up to 227.92. And so that's why we don't have a quality precisely at 50%. Okay? Okay, so this concludes this example problem. And if you have any questions about it, please send me an email or stop by my office. Otherwise, happy thermo.